In this particular lecture, we're going to discuss beats, and beat is is when two speakers. An example of beats is when two speakers play. Their wavelengths are slightly different. The frequencies are slightly different, and we hear this wavering sound. We hear a wavering sound due to the constructive and destructive interference occurring at the same point. So one time, for example, this top picture. These two speakers, they have constructive interference occurring right at this point. But then just a short time later, they have destructive interference occurring at that point. And that's due to the wavelengths being slightly different. So you'll see when the waves come in and they coincide, there's one wave and the other wave, they come together and they get this bigger wave. The amplitude is twice as much. But then when they're shifted over slightly, you'll see that there's destructive interference, and there'll be this red line here that they'll cancel each other out. Here, for example, is the first wave coming along, and the second wave coming along you see is slightly out of phase, it's slightly different wavelength, and you'll see that at this point here, in the beginning point, these two will destructively interfere, so it's small here, it's zero amplitude, and then slowly it gains in amplitude, and now it's loud, and then it's faint, it dies out again, and then it's loud again, and we hear this wavering sound. This wavering sound you will listen to right now. You can hear the destructive and constructive interference patterns. It goes louder, softer, louder, softer. It's the wavering pattern. We call those beats. Now, the number of times per second that wavering occurs is the beat frequency. Here we can see beats actually occur. You'll see the red wave and the blue wave, and there's a dot there showing when they're out of phase and in phase. Right there's destructive interference, and so you'll see that the black dot is small. And as the wave goes along, you'll see that they become more crest to crest or trough to trough, and you'll have constructive interference, and then so on, and then it keeps going that way. The red dot and the red dot and blue dot become 180 degrees out of phase, and then you have destructive interference, and then when they are in phase, you have the constructive interference, and you can see the waves occurring over here as well. So here we have a frequency of 57 hertz, and then the other frequency is 50 hertz. And here's the picture of what those beats would look like. Now what you do is you subtract the two numbers, the 57 minus the 50, and you get 7 hertz. You'll hear 7 beats per second. You'll hear 7 wavers per second. And that wavering sound, and that's simply the beat frequency. And so I can move this to different locations, and you can see the beat frequency. Here it's 51 hertz. Versus 50 hertz. There's a 1 hertz beat frequency. There's a 2 beat frequency. 3, 4, 5, 6, 7, and so on. Here's a typical problem we'll encounter. We have a tuning fork that has a frequency of 500 hertz, and another tuning fork has a frequency of 510 hertz. Find the resulting beat frequency in the beat period. The beat frequency is 510 minus 500, so that's 10 hertz, 10 beats per second. And the period is just 1 over the frequency, so it's 0.1 seconds is the period. You'll hear a beat every 0.1 seconds. So the beats are as straightforward as this. Now they can put beats, and they can make it a more difficult problem. You put the Doppler effect with it and so on. But this is the basic idea with beats.